YouTube now, and you're welcome to start.
Fantastic. All right, so let's do it.
Actually, wait a few seconds because we've got loads of people joining. The numbers of participants are going up quite quickly at the moment, so just give it 2 minutes.
Okay, let's wait. Yeah, that's a good idea. Let's wait a minute.
Oh, and Douglas is getting the latest figures in the chat.
Thanks for those figures, Douglas. And for those on the live stream, the figures coming in are about the conference who's attending. So there's 338 people from the US, 90 from Germany, 87 from the UK, 44 from Switzerland, and 43 from the Netherlands.
Okay, so we're kind of stabling now. I suggest we start.
Yeah, people are still streaming in, but yeah, let's get going. So I see there are over 150 folks on the call, which is great. Okay, let's get started. So welcome everybody to day 4 of RWC, the last day of the conference. Hope everybody's having a great time. I am. I love the program. And to start the day, we're starting with a bang. And so I'm really pleased to introduce Eli Ben-Sasson. Eli, I'm really looking forward to your talk. So Eli is a giant in the area of proof systems and snarks, really wrote so many of the core papers in the area. So Eli, it's really wonderful to have you speak. Eli is also a founding scientist of Zcash and a co-founder of Starkware, and currently is the president of Starkware, and has been doing amazing work in the area on FRI and getting Starks deployed and used in the real world. So Eli, I'm really looking forward to your talk, and the floor is yours. Oh, and before we start, just please everybody remember to post your questions in the Zulip chat, and I'll ask Eli your questions once the talk is over. Eli, all yours.
Thank you so much, Dan, and I thank the program committee for inviting me to speak here. Just to clarify, so I should speak for roughly 25 minutes and leave 5 minutes for questions?
Yeah, that sounds good. Absolutely. Okay. I'm sure there'll be a lot of questions for you. So if you want to do 22
I'll
minutes,
try to pack it in a bit less, and I will share my screen. So here we go. Can you see it?
Yep, all good.
Okay, so I'm going to talk about scaling computations on blockchains with ZK Starks. My name is Eli Ben-Sasson, and I'm co-founder and president of Starkware, a company that currently has roughly a bit over 40 employees. We reside in Israel, and our mission is to bring scalability and privacy to blockchains. So the TLDR of my talk is going to have 3 parts. The main part is going to be the second one. The first one is going to be that, just recalling that blockchains rock. They're really great. You all know that, but they lack scale and privacy. So we want to talk a little bit about mostly the scale. Why is it that this new technology built in the aughts and the teens doesn't reach the scale of other more traditional and older systems? The second part is going to be, saying that we believe that our technology is the right one for solving both of these problems, and it's going to have 3 parts: theoretically, and then practically, and then this is real-world crypto. So I want to tell you about something very accessible that we just released last week, and I hope you'll play with it and use it and build systems with it. This is a language and a framework that we call Cairo. And hopefully the call to action is going to be, please come build on Cairo. And that's the main message. So let's start. And you all know about blockchains, and you know that they don't scale very well, but I want to share my view on why this is the case. So we're all familiar with the good old conventional world that's been serving us for millennia. And it is based on trusted parties, banks, financial institutions, king. And then the integrity of the system is held accountable by humans that we delegate to the process. Regulators, accountants, lawyers, they go and inspect the integrity of the system on our behalf. And this system works, more or less well. Blockchains work very differently. They have a different principle, which is much nicer sounding, and I'll call it inclusive accountability, which translates to anyone with a laptop and internet connection is invited to come over and help inspect the full integrity of all the system. And the motto is verify, don't trust. And I'm saying verify all transactions. You don't want any part not to be verified. So this is a beautiful principle. Because of that, you have two problems. One is privacy, because everyone is verifying all your transactions. And the second one is scalability. So I'm going to focus more on scalability in this part, even though the technology that I'll be presenting can also solve privacy. And usually when people talk about ZKP, so the zero knowledge aspect, of course, covers the privacy aspect. And I'm sure the attendees know this, but I'm going to focus more on scalability, which is what we're aiming to solve first, even though our technology can also address privacy. So there's a huge explosion. ZKPs go back to the seminal work of Goldwasser, Mikali, and Rakov from 1985, which spawned a huge field and thousands of theoretical works. And in the past 10 to 15 years, there's been a real spree of works on implementations of various kinds. And this is not a talk about it. So I wrote a blog post titled "The Cambrian Explosion of ZKPs" that tries to make a little bit of sense of the the way I view the different families of practical implementations, the trade-offs between them. So in these slides that I'll share, there is a link to the post. I also gave a crowdcast on it. So all I want to say is I'm going to be talking only about ZK Starks, but I just want to acknowledge that there are a whole bunch of others, and there's amazing research going on. The reason I'm going to focus on it, other than that's the technology that Starkware is implementing, or the reason why we're focusing on this particular technology, is this TLDR from that talk, that there is a lot of difference between the different members of this huge universe, and they differ by the means they do arithmetization, which is transitioning computational statements to problems about algebraic structures, polynomials usually. There's also a lot of differentiation in the way the different systems tackle low degreeness and polynomial commitment schemes and things like that, and the crypto assumptions that you use to build these systems with. The TLDR that we are working under this premise is that currently for short proofs you want to use something known as Groth16 snarks that power Zcash and many other systems. For everything else, we think Starks are really great. So that's why I'm going to focus on that. And I welcome you to read the blog post and see why we believe in that. So the next part is going to be about this particular region in the space of this huge space of zero knowledge proof systems. And I want to tell you why theoretically ZK Starks are good at solving the scale and privacy problem, and also about how we practically are using them to solve scaling problems, and then how we make them accessible for all of you to come and use these things, even without diving deep into all the crypto and math that underlies it. Okay, so let's talk a little bit about theory. So remember that the main problem we have is that because we want this inclusive accountability, we have these nodes, users with their laptops logging in and verifying all the transactions that are taking place on the network. And this sacrifices privacy and scalability. I'm reminding you that I'm going to focus in this talk only on scalability. So what it boils down to is that each one of these servers or computers or laptops has to process all of these transactions. So each one of these little red squares represents a transaction where Alice is paying Bob, or maybe they're invoking some smart contract or doing some trading, or playing a game on the blockchain. And then what happens is that each one of the nodes that participates in the blockchain has to process each of the transactions and then update the accounts or the UTXO set and update the state of the system so that you solve a state replication problem in some way. And there's a whole area of consensus. How do you know that how do you incentivize all nodes to reach consensus? That's not part of this talk, but I'm just focusing on the aspect of verifying transactions. So currently, the way the system works is that each one of these, inclusive accountability nodes, you come on with your laptop, you're going to process all the transactions that go and check all the signatures, update the accounts. And this is, of course, this doesn't scale very well. And this is the answer to the question that I posted at the beginning. Why is it that Bitcoin launched in 2008 or Ethereum, launched in 2015, do not reach the scale of Visa or Swift or FIPS or any one of these older systems that actually relies on technology from the 70s. The answer to that question is not because there aren't big enough computers that can process 1,000 transactions per second or 10,000 transactions per second for Ethereum. That's not the problem. The problem is that your laptop can't do it, right? So the Visa network has some big servers that it's a trusted party model that can process 10,000 transactions per second. But if you want all laptops to do this while you're also tweeting or blogging or doing something else without your computer heating up, you're going to have to limit the number of transactions per second, or the amount of computation that each one of these nodes is doing. And that's the reason they don't have very high scale. Okay. So how can ZK Starks or other scalable ZKPs solve this problem? So let's recall briefly what is a proof system. So you have the privacy aspect, which means that a proof, once generated, does not reveal anything about the private inputs that go into it. As I said, zero knowledge is a very important aspect of ZKPs, but it's not going to be the one that I'm going to focus on today. Let's talk about scalability. So scalability, I'm going to mathematically define it as a proof system. I'll call it scalable if it achieves two things simultaneously. The proving time scales quasi-linearly, which means like n log n, where n is the amount of computation that is processed. And simultaneously, the verification time scales polylogarithmically with n. So if you have a system that achieves both of these properties, both quasi-linear proving time and polylogarithmic verification time, I'll call it scalable. And Starks are one family of proof systems that are scalable. So if you have a scalable proof system, you can have your prover processing the transactions and then generating a proof that is exponentially smaller than the amount of computation that would go into verifying all transactions, and then send this proof to verifiers that are going to work exponentially less hard than the prover works. So the prover is going to be some big machine, but because of the beautiful cryptography and math and complexity theory behind it, the prover, even if it's malicious, cannot really cheat the verifier, right? This won't work, right? Cryptography is going to prevent that. So you don't need to trust the prover. It doesn't have to be part of the system of nodes that is part of your network. So now let's apply it to blockchain. We're going to take the verifiers and put them on each one of these laptops that participates in the public blockchain. And now each one of these nodes doesn't have to maintain the whole set of the accounts. It can just maintain, let's say, a Merkle root for some other hash of the state of the system. And then the prover is going to be the only one getting the transactions and processing them. And it will also get the previous, the current root of the system. And it will generate, compute the new root to which the system is now transitioning, and generate a proof of computational integrity and send it to the blockchain. So now what the verifiers need to do, they just need to take as input the previous root, the current root, the proposed new root, and a proof. And if the proof is verified correctly, and this is exponentially faster than verifying the transactions, each one of these nodes can move on to can now replace the state of the system with a new state, and thereby exponentially save on the amount of computation. So if we go this way, we can retain the beautiful principle of inclusive accountability, but we can exponentially scale the amount of computation that is processed by the network. We are going to offload the bulk of the work of generating a proof to the prover, and the verifiers only need to verify the correctness of the proof, which is exponentially faster. So this is the theory. Okay. Now, you updated from the old Merkle roots, which are in blue, you updated them to the new Merkle roots, which are in red, and then you repeat this process. Now, I just want to go over some other things that go into a Stark, that Starks and other ZKPs share. they're universal, and universality is going to be the main topic of the next part of the talk. They apply to any computation, not just to payments or not just to particular protocols. You can take any computer program and prove its computational integrity. The T in the definition of Stark stands for transparency, which means all messages, from a mathematical point of view, it means that all messages coming from the verifier are basically public randomness. These are also known as Arthur Merlin protocols or public coins. And some Starks, in particular the one that my company is building, rely only on the existence of some collision-resistant hash function. So they're lean and battle-hardened cryptography, meaning that they rely on things like the security of SHA-2 or any other hash function, which is pretty much one of the most basic premises of security in our world today. So I said I'm not going to go into an exploration of the big universe of ZKPs. A very popular term is SNARK. So I just want to point out briefly the difference between the two. So the S in SNARK stands for succinctness, which is not exactly scalability. It means you want exponentially small verify running time, but you allow post-processing. You allow pre-processing that could be linear in the size of the computation or even more. In the case of Stark, this is forbidden. And the definition of a SNARK does not necessarily say that the prover must be efficient. It could be quadratic time or larger, even though a lot of the very efficient SNARKs are actually quasi-linear proving time. Another thing is that the N means non-interactive. So it's a single shot proof in the common reference string model. And I just want to point out that one of the reasons we think Starks are slightly better than SNARKs is that if you came up with a Stark, you can always apply the fiat Shamir, or the Mikali, and then there's a transformation in a paper with Chiesa and Nick Spooner that shows how you can transform any one of these Starks into a Snark, but not always can you go in the other direction. So that's a little bit on the difference between the two. So now I want to talk a little bit about practically. I talked about the theory, how theoretically ZKPs or ZK Starks could help solving the problem at hand of scalability. So now I want to talk a little bit about practically. So Ethereum and other blockchains can process roughly 4 trades per second and 30 payments per second. Our systems that are currently deployed and serving customers can reach 9,000 trades per second and 18,000 payments per second. These are production systems that are now working. We also went even a bit further and displayed how you can process 300,000 transactions in a single Stark proof that was deployed on mainnet Ethereum. That was in the context of convincing Reddit that they can take all of its point systems and use our system for it. That's 3,000 TPS, whereas Ethereum, even if it would only deal with payments, would only reach 30 TPS. And so this is about practicality. Now, how do we build such systems? And now I want to go to the accessibility and how we made it accessible for everyone to start building Starks. So you start with a computational integrity statement, something you want to prove. Let's say I processed 10,000 trades and now I need to update the Merkle root accordingly. And you're going to transition and move it into something that we call an AIR, an algebraic intermediate representation. And from there, you're going to apply low degree testing and then some cryptography and make it into a Stark, and you get your proof. The main thing I want to point out is that the left part of this picture depends on the CI statement. So if you're talking about payments, it's one AIR. If you're talking about trades, it's another AIR, and so on and so forth. And the rightmost part that has a lot of algebra and the crypto does not depend on the statement. So currently, the way we went about writing these Stark systems is we had to construct this AIR, which is a bunch of constraints that each one of them is a polynomial, and we need to define some execution trace that is a table of field elements, and this is very cumbersome. Here's a picture of one of the visualization tools that our engineers built in order to deal with such things. So, this sort of shows you the different trace cells that we have in a computation and shows a particular constraint, and you can write by hand constraints for various computations. So every different computational integrity statement resulted in a different error, and you had to handwrite these things and try to minimize the size of the trace, the number of rows, the number of columns, the degree of the constraints. And of course, as the logic got more and more complicated, you would have to worry about debugging. How do you document this? How do you audit it? What about reusing pieces of code, modifying it, making optimizations? It all becomes very hard. It's a little bit like building an ASIC, right? A chip by hand. It's maybe very efficient if you know how to do it, but it doesn't scale very well in terms of code complexity. So now we reach Cairo, which is our new thing that was released last week. So Cairo stands for CPU Air. What if you had a compiler that could take a computational integrity statement written in a high-level programming language and then convert it to input that always goes to one single error? And the error of Cairo has less than 50 columns or trace cells. That's its W. The number of constraints is well below 100. The degree of each one of these constraints is 2. The length of the trace depends on the program that you're running, but it's one error to rule them all, meaning every program you can think about, you can write it in a way that it will be compiled and sent to this one algebraic intermediate representation. So Cairo is the first universal von Neumann start, which means the first proof system that is scalable, transparent, universal in von Neumann architecture released. It is also the first universal von Neumann verifier that actually sits on a blockchain, on Ethereum mainnet. So it's one smart contract that verifies any computer program written in Cairo. And I just want to mention that there's an abundance of works on universal ZKPs of various forms. There's a good reference for it on ZKP Science. I'm not going to survey all of them, but Cairo is the first universal von Neumann start, first universal von Neumann verifier on a blockchain. Now I want to get to the meat and tell you how you can, what you should be doing, or I hope you'll be doing, some of you. So Cairo is, let's call it a minimal viable language. For what? For reaching production-grade Stark systems. We applied the Goldilocks principle, which is, not too cold, not too hot. So the virtual machine underlying Cairo only has 3 registers: a PC, an allocation pointer, and a frame pointer. It has a very minimalistic instruction set, but it supports functions, recursion, branching, conditionals, access to random memory. You see here some snippets and library functions for it. And we actually are building all of our production systems, the ones that are running today, the ones that will be deployed over the next month or two, using this language. And we released the Cairo code for them. So we just released last week a full tool chain that includes a compiler, a virtual machine, IDE extensions, tracer, which is sort of a debugger, and we released the source for our application code, the one that we are running in production on Ethereum today for scaling spot trading, and we'll release similarly codes for margin trading and for non-fungible tokens. Cairo turns out to be pretty efficient because even though a CPU is less efficient than an ASIC, the fact that you allow your developers to write complex optimizations in a safe way because they're writing in a high-level programming language and not putting constraints by hand means that you end up with much more efficient code in practice. So it's even efficient. So the next steps for us, we're going to do a lot of Cairo education. This is something we started last week. We're going to put a proving service on testnet probably in 2 to 3 weeks' time that you can sort of write code, press a button, have that appearing and verified on blockchain. Later on, we're going to put a proving service on mainnet. Maybe we're going to decentralize the proving ecosystem so that not only we are the ones running our provers. And what you should do is visit the Cairo Playground that I'm now going to show to you. And you should write Cairo code, and you should later on deploy your scalable app with Cairo. So I just want to show you the Cairo Playground. It's accessible. The link is there. You can see here examples of Cairo programs. Here, a bunch of challenges that teach you things. You can sort of load a program, run it, Okay, I got an error here, but you know, you never use never use the internet or try to run anything. But here's an example of a program that is output. You can sort of go over the various steps of the program, understand what's going on, learn it, and I guess the very last thing I just want to say is that if there's one thing you should do, you should try out the Cairo Playground now for yourself. Because again, just to tie the story, if you write code in this system, within 2 to 3 weeks, you can press a button and that code will have star proofs of it generated and placed and verified on a blockchain. And this will lead the way for you to build systems like we are building. The systems we are building are built in Cairo, written in Cairo. So you can write your scalable systems, and then you will have the ability to reach the scale that currently we are reaching. And that's something that we very much like to see. So thank you very much. Happy to answer any questions.
Wow, awesome. Thank you, Eli. This is fantastic. Very impressive. Maybe I could just say there are a couple of questions, but let me take my role as a moderator and ask the first couple of questions. First of all, it sounds like there's a really cool deployment scenario here where the verifier is going to be deployed as an Ethereum library in effect. And then new contracts, I guess, wouldn't even have to implement the verifier themselves. They can just call your verifier and verify whatever proofs they have to verify. That's kind of the plan of how this would work?
That's not just the plan. That's the way we are working right now. There is a single Cairo verifier. Our StarkX systems are currently basically code, Cairo code, and we send the Cairo code along with the computational integrity statement to this one Cairo verifier smart contract. Yes. So and all
great.
programs are going to be sent to it, has one single heir and one single smart contract.
Yeah, that's fantastic. So first question is, Cairo is sort of a specific domain-specific language, right? A specific DSL for verifiers. I'm just curious, like, what's your take on these languages? There are many domain-specific languages, DSLs, that have been developed now for proof systems. There's Socrates, there's Zing, there's Snarky. Where does why did you decide to design a new language? Why not use one of the existing languages? Or where does Cairo fit in all the ecosystem of languages that have been developed for proof systems?
Right. So I think I wouldn't treat it as a DSL. It's a little bit more like an assembly language with a CPU that is, Turing complete and universal. It has all the, nice attributes that you would think of a full-blown, programming language. So it allows you memory access, recursion, branching. You can write libraries. So I think DSLs are a bit, So I don't know, when I think of a DSL, I think of something that by design is not Turing complete, cannot process all programs there are there. This can really, any logic that you have. So in that sense, it's a little bit similar. I mean, and we saw a few of those. I mean, there's, TinyRAM, and there are compilers from C to various circuits. So it's a bit more similar to that. In this respect, it's I think the main things. So there were previously other universal proof systems. Conversions from universal languages to proof systems. What's most unique about this, I think, is the sort of production grade and integration with blockchain. So it doesn't do, once you have universality, you can process any program. So it doesn't.
This is as real world as it gets. We have a couple other questions. John Zhu.
We're building our systems and deploying them using this framework. Yes.
Yeah, for sure. Yeah. So John is asking, does this apply to Bitcoin in any way?
Okay, Bitcoin, we'd love to place this capability or any Stark capability on Bitcoin. That would require Bitcoin, being able to have a Stark verifier on of some sort. And we'd love to work with the Bitcoin community to make that happen. Currently, I think the Bitcoin community is rather conservative, and the things are deployed rather slowly on it. But there's so currently, no, you can't put it on Bitcoin, but I really hope that Bitcoin will someday adopt, allow us Stark
Maybe there'll be an
verifier.
opcode that says verify Stark.
Yes, yes, yeah.
That would be the natural way, I guess, to incorporate
Yes.
it. Let's see. So Jake is asking, how has your view of the differences between Starks and Snarks changed over the last year, with the latest research beginning to allow transparency for Snarks too?
I think there's a lot of tremendous research on all ZKPs, and it will continue. I still think that in terms, I still stand by what I said previously, which is that if you want, if the length of the argument is the thing you want to minimize, then Groth 16 is the king, and maybe other systems that are, some of them transparent or coming close to that, but then I think that, to best of my knowledge, all other aspects, which mean proving time, verifying time, and minimality of crypto assumptions are best in this sort of what we call their air fry Starks. But that's my still my view.
Yeah, it makes sense. Basically, yeah, that's a fair answer. So I want to actually end. We're actually at time, but I want to end with something that I think is a research question. So let me ask you this, and it's fine to say that there is no answer. So the prover architecture that you mentioned basically allows everybody to submit their transactions to the prover, and then the prover submits basically the log of transactions and a proof to the blockchain, and now the blockchain just verifies the proof rather than verifying 10,000 transactions. But this gives the prover some power, in that the prover can choose the order in which transactions are submitted to the chain. So for example, if a bunch of transactions are submitted, the prover can basically front run all those transactions by inserting its own transaction first.
Right.
So do you see in this prover architecture, do you see a way to it seems like front running is sort of inherent in this transaction. Do you see a way to prevent front running in this environment?
Currently, the way we think about it right now is we are saying there is a separate question of sequencing sequencing / operating, which means who or how do you sequence the transactions. There are many. So currently, we are not. First of all, we are not solving these problems. On our systems, there is an operator, so it is the one that is sequencing. In other variations, it's going to be there's the term ZK rollup, which basically means that people are going to submit, you're going to put the sequencing on the blockchain. So it doesn't solve the problem, it just pushes it to some other area. Right now, you let the blockchain sequence it, and then you have a prover just taking the sequence from there, and sort of it's committed to processing in that order. But to answer your question about am I aware, or are we conducting research on using ZKPs to solve the sequencing problem or decentralized sequencing in a better way? The answer to that is no. I think it's a terrific direction, but and Starkle, we haven't spent any resources on thinking about it. But Dan, as usually, you're leading to very interesting questions. So I hope someone.
Yeah, it's a great question for the community.
Yes.
All right, so fantastic. So we're at time. Thank you so much, Ellie. This was really great. So thank you.
And I'll post